China's launch of the world's first thorium-based molten salt reactor is a significant milestone in the evolution of nuclear energy. This reactor, using thorium as a fuel source, has the potential to transform how nuclear energy is produced. Thorium is more abundant and produces less long-lived radioactive waste compared to uranium, making it a more sustainable option. Moreover, the molten salt technology enhances safety by operating at lower pressures and temperatures, drastically reducing the risk of catastrophic failures like meltdowns. China's development of the world's first thorium-based molten salt reactor places it at the forefront of nuclear technology, setting new standards for innovation. This reactor design offers several key advantages, such as continuous refueling capabilities, which reduce operational downtime and allow for more efficient energy production. The ability to manage nuclear waste more effectively is a significant environmental benefit as it minimizes long-term radioactive hazards. Furthermore, the reactor's operation at higher temperatures enhances electricity generation efficiency, making it economically more attractive compared to traditional nuclear reactors. The molten salt technology used in this reactor also provides superior heat management. This capability not only improves the safety of the reactor by reducing the likelihood of overheating, but also allows the system to be integrated with other renewable energy sources, such as solar or wind power. This integration can help create a more resilient and flexible energy grid, capable of adapting to fluctuations in energy demand and supply. Moreover, the higher operational temperature of the reactor allows for more efficient thermal energy conversion, which can lead to lower costs per unit of electricity produced. This makes thorium reactors not just a cleaner alternative, but also a potentially more cost-effective one in the long term. The ability to continuously refuel without shutting down the reactor adds to this economic efficiency as it reduces the time and resources needed for maintenance. China's pioneering work with thorium reactors could influence global nuclear energy strategies. As countries seek to transition to cleaner energy sources, the success of China's thorium reactor could encourage other nations to invest in similar technologies. This could lead to a global shift away from uranium-based reactors, which carry more significant environmental and geopolitical risks, towards thorium, which offers a safer and more abundant alternative. In the broader context of energy security, thorium reactors could play a crucial role in reducing reliance on fossil fuels. By providing a stable and reliable source of energy, they can help countries achieve energy independence and reduce their carbon emissions, contributing to global climate goals. The ability to integrate with renewable energy sources further enhances the role of thorium reactors in a sustainable energy future. China's advancements in thorium reactor technology also have the potential to reshape the global energy market. By positioning itself as a leader in this area, China could become a key exporter of thorium reactor technology, influencing global energy policies and fostering new international partnerships. This could also spur competition among other countries to develop their own thorium reactors, accelerating innovation and potentially leading to new breakthroughs in nuclear energy. China's launch of the world's first thorium-based molten salt reactor is a significant milestone in the evolution of nuclear energy. It offers a promising alternative to traditional uranium reactors, with benefits that include improved safety, efficiency, and environmental impact. If successful, this technology could pave the way for a new era of clean, sustainable, and economically viable nuclear power, with far-reaching implications for global energy strategies and environmental sustainability. China's investment in thorium reactors represents a pivotal shift in global energy strategy, potentially setting a new standard for nuclear power that aligns with worldwide carbon reduction goals. Thorium, being more abundant and less hazardous than uranium, offers a more sustainable alternative, reducing the risks associated with nuclear energy, including the proliferation of nuclear weapons. China's success could accelerate global adoption as countries strive to reduce fossil fuel dependency and transition to cleaner energy sources. This move also positions China as a leader in the global energy transition, emphasizing its commitment to innovation in sustainable technologies. Furthermore, China's thorium reactor project aligns with its broader goal of achieving energy security while meeting climate commitments. The technology could significantly contribute to reducing carbon emissions, which is crucial in the fight against climate change. As other nations observe China's progress, they might consider adopting similar strategies, potentially leading to a global shift towards thorium-based nuclear power. This could foster international collaborations aimed at advancing nuclear technology, thereby accelerating the global transition to a low-carbon future. In addition, thorium reactors' ability to integrate with renewable energy sources makes them a key component of a diversified energy mix. This integration not only enhances energy security by reducing reliance on a single energy source, but also supports the stability and resilience of the energy grid. The global energy landscape could be transformed as more countries adopt this technology, leading to increased competition and innovation in the nuclear sector. As China continues to develop its thorium reactor technology, it is likely to influence global energy policies and strategies. Countries with significant thorium reserves, like India and Brazil, may also invest in this technology, leveraging their natural resources to enhance their energy security and sustainability. This could lead to the formation of new international alliances centered around thorium technology, further reshaping the global energy market. China's thorium reactor initiative is not just a technological advancement, but a strategic move that could redefine the future of nuclear energy. If successful, it could usher in a new era of safer, cleaner, and more efficient energy production, positioning thorium as a cornerstone of the global energy transition. The implications of this development are vast. For one, it could lead to a decrease in the proliferation of nuclear weapons, as thorium cannot be easily weaponized. Moreover, it could inspire other nations to invest in similar technologies, potentially leading to a new era of nuclear power that is safer, more efficient, and more sustainable. This shift could significantly alter the global energy landscape, reducing the geopolitical tensions associated with energy resources and contributing to global energy security. In the long term, China's advancement in thorium-based nuclear technology could pave the way for widespread adoption of this safer, cleaner form of nuclear energy, positioning it as a cornerstone in the fight against climate change and the global push towards a sustainable energy future. Uranium has long been the cornerstone of nuclear reactor technology due to its exceptional energy density and ability to sustain nuclear fission reactions. This high energy density means that even small quantities of uranium can produce vast amounts of energy, making it a highly efficient fuel source for generating electricity in nuclear power plants. The fissile isotope uranium-235 is particularly valuable because it can easily sustain a chain reaction, where each fission event releases neutrons that continue to propagate the reaction, thereby generating continuous energy output. Despite these advantages, the use of uranium in nuclear reactors is fraught with significant risks and challenges. One of the most pressing concerns is the potential for severe nuclear accidents, which can have catastrophic consequences for both human populations and the environment. Historical incidents such as the Chernobyl disaster in 1986, the 3 Mile Island accident in 1979, and the Fukushima Daiichi nuclear disaster in 2011 vividly illustrate the dangers inherent in nuclear power generation. These events resulted in the release of large amounts of radioactive materials into the environment, leading to immediate loss of life, long-term health issues such as cancer, and extensive environmental contamination. The psychological and economic impacts of these disasters have also been profound, contributing to public fear and opposition to nuclear energy. Another major issue associated with uranium-based reactors is the generation of long-lived radioactive waste. When uranium-235 undergoes fission, it produces a variety of fission products, many of which are highly radioactive and have long half-lives, meaning they remain hazardous for thousands to millions of years. This radioactive waste poses a significant challenge for disposal and long-term storage. Current strategies for managing this waste involve deep geological repositories, which are designed to isolate the radioactive materials from the biosphere for extended periods. However, the technical complexities, high costs, and societal and political challenges. Thorium presents a highly promising alternative to uranium in nuclear energy production for several reasons. Firstly, it is more abundant in the Earth's crust, making it a more accessible and potentially less expensive resource. Unlike uranium, thorium's nuclear reaction process produces significantly less radioactive waste, which is a major advantage in terms of environmental safety and waste management. Additionally, thorium's byproducts are less toxic and remain radioactive for a shorter period compared to uranium waste. One of the most significant benefits of thorium is its reduced potential for weaponization. Unlike uranium-235, which can be easily enriched to produce weapons-grade material, the thorium fuel cycle does not naturally produce plutonium or other materials that are easily weaponized. This makes thorium a less attractive option for nuclear proliferation, reducing the geopolitical risks associated with nuclear energy development. In terms of safety, thorium reactors have an inherent advantage due to the nature of the nuclear reactions involved. Thorium's nuclear reaction is easier to control, which greatly reduces the risk of catastrophic events like meltdowns. This is partly because thorium reactors can operate at lower pressures and temperatures compared to uranium reactors, and they often utilize molten salt technology, which provides an additional layer of safety by allowing for more effective heat dissipation and reducing the likelihood of explosive failures. These factors combined make thorium an appealing option for the future of nuclear energy. It offers a pathway to safer, more sustainable nuclear power that addresses many of the concerns associated with traditional uranium-based reactors. China's recent launch of the world's first thorium-based molten salt reactor could be a significant step toward realizing the potential of thorium, positioning it as a viable and attractive alternative to uranium for global energy needs. This development has the potential to reshape the nuclear energy landscape, reducing the environmental impact, enhancing safety, and minimizing the risks of nuclear proliferation. The design of thorium reactors is central to their enhanced safety and efficiency compared to traditional nuclear reactors. Instead of using solid fuel rods and water as a coolant, thorium reactors utilize a molten salt mixture, which serves dual purposes. As a coolant and as the medium in which thorium fuel is dissolved, this molten salt mixture has a much higher boiling point than water, which eliminates the need for high-pressure systems and significantly reduces the risk of explosive failures. The molten salt also circulates continuously through the reactor, allowing for more uniform heat distribution and reducing the chances of hotspots that could lead to structural damage. Additionally, this design enables the reactor to operate at lower pressures and temperatures, which inherently makes the reactor safer and less prone to catastrophic failure. Another advantage of using molten salt is the ability to continuously add fuel and remove waste without shutting down the reactor. This continuous operation not only improves the efficiency of the reactor, but also helps in managing radioactive byproducts more effectively, preventing the buildup of dangerous materials that could destabilize the reactor. In the event of a system failure, many thorium reactors are designed with a freeze plug safety feature. This plug is kept solid by an external cooling system, and if the system fails, the plug melts, allowing the molten salt and fuel to drain into a subcritical storage tank, effectively shutting down the reactor and preventing a meltdown. These features combined make thorium reactors a promising alternative for safer, more efficient nuclear energy, potentially transforming the future of global energy production. In a molten salt reactor, the process of nuclear fission occurs when thorium atoms are bombarded with neutrons, transforming them into uranium-233, a fissile material that sustains the chain reaction. As the fission process unfolds, it generates substantial heat, which is absorbed by the molten salt mixture, acting as both a coolant and a medium for the thorium. This heated salt is then pumped through the reactor, where its heat is transferred to a secondary coolant loop. This secondary loop typically involves a conventional steam cycle, where the heat converts water into steam, which then drives turbines to generate electricity. This design not only allows for efficient heat transfer, but also offers enhanced safety. The use of molten salt as both coolant and fuel medium means the reactor can operate at lower pressures, reducing the risk of explosions. Additionally, the continuous flow of molten salt helps to prevent localized overheating and allows for the continuous removal of fission byproducts, making the reactor more stable and reducing the risks associated with radioactive waste accumulation. One of the most significant advantages of this system is its safety. The molten salt has a very high boiling point, meaning it remains liquid at much higher temperatures than water. This eliminates the need for high-pressure containment systems, which are a critical safety risk in traditional reactors. Moreover, if the reactor core were to overheat, a freeze plug at the bottom of the reactor would melt, allowing the molten salt to drain into a containment vessel where the reaction would safely stop. China's new thorium reactor, located in the remote Gobi Desert, represents a significant leap forward in nuclear energy technology. As the first commercial thorium reactor, it is expected to play a pivotal role in China's ambitious energy transition strategy. By harnessing thorium, which is more abundant and produces less hazardous waste than uranium, China aims to reduce its dependence on coal and significantly lower its carbon emissions. This reactor could provide a stable, low-carbon energy supply for China for many decades, leveraging the country's substantial thorium reserves. The strategic placement in the Gobi Desert not only capitalizes on the vast, sparsely populated area, but also underscores China's commitment to exploring innovative energy solutions in its quest for carbon neutrality and global leadership in clean energy technologies. This development may also influence global nuclear energy policies, potentially leading other nations to explore thorium as a viable alternative to traditional uranium-based reactors. The Gobi Desert location is strategic, not just for its isolation in case of an accident, but because the reactor's design does not require water for cooling, making it ideal for deployment in arid regions. The initial reactor is relatively small, with a capacity of just 2 megawatts, but China has ambitious plans to scale up this technology. Future reactors could generate much more power and be deployed across China and potentially in other countries as part of China's Belt and Road Initiative. The launch of the world's first thorium reactor in China holds profound global implications, particularly for the future of energy production. If this technology proves to be as safe and efficient as its advocates suggest, it could revolutionize how countries approach nuclear energy, making it a more attractive option for those aiming to reduce their carbon emissions without the severe risks associated with uranium-based nuclear power. The success of thorium reactors could shift the global energy landscape, offering a cleaner, safer alternative that helps nations meet their climate goals while maintaining energy security. This could lead to widespread adoption of thorium technology, sparking a new era of nuclear energy that balances power generation with environmental responsibility. The shift could also reduce global reliance on fossil fuels, contributing significantly to the fight against climate change and offering a promising path forward for sustainable energy development on a global scale. This development also has strategic implications. By leading in the development of thorium technology, China could gain a significant geopolitical advantage. The ability to offer a safer, more sustainable form of nuclear power could bolster China's influence in global energy markets, especially in developing countries that are part of China's Belt and Road Initiative. Despite the promise of thorium reactors, there are still significant challenges to overcome. For one, the technology is still in its infancy, and it will take years of research and development before thorium reactors can be widely deployed. Additionally, there are technical challenges related to the corrosive nature of molten salt, which can damage reactor components over time. Regulatory challenges are significant for thorium reactors. Since they operate on different principles than traditional uranium reactors, existing safety standards and protocols are not directly applicable. This necessitates the development of new regulatory frameworks to ensure safe operation. Moreover, while thorium reactors generate less radioactive waste than their uranium counterparts, the waste that is produced still requires careful management and secure storage to prevent environmental contamination. Establishing protocols for handling this waste, alongside the unique operational aspects of thorium reactors, is crucial for their widespread adoption. Additionally, the development of thorium reactors will likely require substantial investment in research and development to address these regulatory challenges. This includes creating robust monitoring systems to ensure reactor safety and developing secure long-term waste storage solutions. The global nuclear regulatory community must collaborate to establish standardized safety and waste management protocols that can be implemented internationally, facilitating the safe and effective use of thorium technology across borders. The success of China's thorium reactor could serve as a model for other countries, demonstrating the feasibility of thorium as a safe and sustainable alternative to traditional nuclear power. However, the pace at which thorium reactors can be adopted will depend heavily on overcoming these regulatory and waste management hurdles, ensuring that the technology meets the highest safety standards before it can be deployed on a global scale. The potential benefits of thorium reactors extend far beyond the borders of China. If these reactors can be successfully developed and deployed, they could offer a revolutionary shift in how the world generates nuclear energy. Thorium's abundance and safety profile make it an attractive alternative to uranium, with the potential to significantly reduce the environmental and geopolitical risks associated with nuclear power. Additionally, thorium reactors could play a critical role in global efforts to combat climate change by providing a low-carbon energy source that is both reliable and scalable. However, the road to widespread adoption of thorium technology is not without its challenges. One of the primary hurdles is the need for a new regulatory framework that can address the unique operational aspects of thorium reactors. These reactors differ significantly from traditional uranium-based reactors in both their design and function, necessitating the development of new safety standards and protocols. Ensuring the safe operation of these reactors, especially in the early stages of deployment, will require rigorous testing in a robust regulatory environment. Another challenge lies in managing the nuclear waste produced by thorium reactors. While it is true that thorium reactors generate significantly less waste than their uranium counterparts, the waste they do produce still needs to be carefully managed. This waste, although less radioactive and with a shorter half-life, still poses risks that must be addressed through secure storage solutions and disposal methods. Developing these waste management strategies will be critical to ensuring the long-term viability of thorium-based nuclear energy. Furthermore, the international implications of China's advancements in thorium technology are profound. As other nations observe China's progress, they may be encouraged to invest in their own thorium reactor programs. This could lead to a global shift towards thorium as the preferred nuclear fuel, especially in countries looking to reduce their carbon emissions without the risks associated with uranium. Such a shift would require international collaboration on research, development, and the establishment of standardized regulations to govern the safe use of thorium reactors worldwide. The success of China's thorium reactor could profoundly impact global energy economics by altering the balance of power in energy markets, particularly in regions that are currently heavily reliant on coal and other fossil fuels. As thorium becomes a more widely accepted and utilized energy source, it could drive a significant reduction in global reliance on carbon-intensive fuels. This shift would not only contribute to achieving international climate goals, but also encourage the development of a more sustainable and resilient energy infrastructure worldwide. The economic implications are vast. As countries increasingly adopt thorium technology, the demand for coal, oil, and natural gas could decline, leading to a potential decrease in the global prices of these resources. This shift might also catalyze the growth of industries related to thorium mining, reactor construction, and maintenance, creating new economic opportunities and jobs. Additionally, countries that invest early in thorium technology could gain a competitive advantage in the global energy market, positioning themselves as leaders in the next generation of nuclear power. Moreover, the scalability of thorium reactors could make them particularly attractive to developing nations looking to expand their energy infrastructure without the environmental downsides of fossil fuels. As thorium reactors produce less long-lived radioactive waste and are less prone to accidents, they could offer a safer and more sustainable alternative to traditional nuclear power, making them an appealing choice for countries aiming to meet growing energy demands while also addressing climate change. In the broader context of international relations, the rise of thorium as a key energy resource could shift geopolitical dynamics, particularly in regions where energy security is a critical concern. Countries with significant thorium reserves may find themselves in a stronger bargaining position, while those reliant on imported fossil fuels might seek to diversify their energy sources to include thorium. This could lead to new alliances and partnerships focused on the development and deployment of thorium technology, further influencing global energy policies and strategies. China's success with thorium reactors has the potential to be a game-changer in the global energy market, driving both economic and environmental benefits on a scale that could reshape the future of energy production and consumption. While there are considerable challenges to overcome, the successful development and deployment of thorium reactors hold the promise of transforming the nuclear energy landscape. By providing a safer, more sustainable, and less geopolitically fraught alternative to uranium, thorium could play a pivotal role in meeting the world's growing energy needs while mitigating the environmental impact of energy production. The global community will be closely watching China's progress in this area, as the implications of their success could reshape the future of energy on a global scale.